In this section, we will apply the F35 and F60 feeder protective relays to an application that will develop in several steps. Each step will build on the last such that all of the following common feeder elements will have been utilized. Phase time over current, ANSI device number 51P. Phase instantaneous over current, ANSI device number 50P. Phase directional over current, ANSI device number 67P. Neutral or ground time over current, ANSI device number 50N or 50G. And neutral or ground directional over current, ANSI device number 67N or 67G. We will start our first application with a radial distribution system which includes a generator, 2 buses, and some feeders. Adequate protection of this system can be achieved with non-directional overcurrent elements supported by both the F60 and F35 relays and the principle of time overcurrent grading. This application will cover overcurrent coordination for a radial distribution system using the principle of time overcurrent grading. The customer has chosen F60s to protect their radial distribution system. In order to accomplish this, we must calculate the settings for the elements within the F60 relays such that correct coordination and selectivity is established between the F60s and the fusing. We note that the system does not have a dedicated ground CT for each relay, and so neutral as opposed to ground overcurrent protection will be used. For radial systems, the procedure is to perform the short circuit study from the source to the load furthest away from the load. We then study the coordination from the zone of protection furthest from the source and work backwards to the source. To perform the short circuit study, the engineer must obtain the system information. For our example system, the data is as follows. The line between bus 1 and bus 2 is 10 kilometers in length and has a line impedance of 0.96 ohms. The line from bus 2 to the end is 6 kilometers and has a line impedance of 0.72 ohms. The protection engineer then converts this radial distribution system data into per unit with the following base values. Base MVA equals 10 MVA, and base kilovolts equal 11 kilovolts. The next step is to calculate the fault currents at different locations using ETAP or equivalent software. The short circuit study of the system allows the protection engineer to easily determine the maximum short circuit currents for faults at locations F1, F2, F3, and F4. Note that the generator output power will vary, and so the protection engineer must keep this in mind to ensure that the settings for the primary and backup protection work for minimum fault current levels. For faults beyond or to breaker 52.2, the calculations for the overcurrent protective elements are fairly straightforward. The same isn't true to distinguish between faults on either side of breaker 52.2. For faults at F2 or F3, the fault currents are almost the same. There is no way to achieve selectivity on the basis of current magnitude alone. The most cost-effective solution is to use coordinated time delays. This strategy is known as time overcurrent grading. Let's go further. As stated earlier, we should start with the zone of protection furthest from the source, and so we will start with the relay F60 II. The load on bus 3 is 5 MVA. The overcurrent protection elements of relay F60 II must be coordinated with the highest rated fuse on bus 3, which is FS1. The operating characteristic FS1 is 75 amps at 11 kilovolts voltage. FS1's thermal damage curve is as shown. Relay F60 II's protection should be configured to trip for any fault on the line beyond breaker 52.2 over the complete range of generator output power and be properly time coordinated with the fuse curve. Relay F60 II's protection should be configured to trip for any fault on the line beyond breaker 52.2 over the complete range of generator output power and be properly time coordinated with the fuse curve. Now we will determine the pickup setting for the F60 II phase time over current, or TOC for short. First, we need to calculate the maximum load current. Remember that within the universal relay, the pickups are set in per unit values. The F60 II relay has a 600 to 5 CT, and so 1 per unit within this relay is 600 amps. Now we're going to calculate F60 II's maximum load current. 5 MVA divided by root 3 times 11 kilovolts equals 262 amps. From this calculation, we can see that the maximum load current is 262 amps. By convention, the minimum pickup for the time over current setting should be set to twice the maximum load current, or in this case, 524 amps, which is 0.873 per unit. This pickup level is then checked to see if it is lower than fault currents at both the beginning and end of the zone of protection. The first check is to compare this setting to the maximum fault current at F3, which is 2,133 amps, or 2,133 divided by 600, which equals 3.55 per unit. This fault current is higher than the pickup that has been chosen, and so this setting will work for faults at F3. The maximum fault current at F4 is 1,613 amps, or 1,613 divided by 600, which equals 2.69 per unit. Finally, we check to ensure that the minimum fault current at F4, for example 80% of F4's maximum fault current, or 1,290 amps, is higher than F60 II's TOC pickup of 524 amps, or 0.874 per unit. We can conclude that a pickup of 524 amps is appropriate for all fault conditions. We will now determine the F60 II's phase time over current multiplier. Since the F60 II is the last relay in the radial system, we must coordinate only with the highest rated fuse on the downstream side. This is the transformer fuse FS1, which is rated for 75 amps. The IEEE extremely inverse characteristic slope best matches the clearing curve of this fuse, and so this curve will be used. Earlier in the course, it was determined that to account for CT saturation, timing errors, and fuse errors, a minimum discrimination time of 0.3 to 0.4 seconds between the relay and fuse curves should be used. To determine the value of the time dial or time multiplier, we use the IEEE extremely inverse characteristics formula and work backwards. We want an operating time of 0.4 seconds to give a 0.3 second separation between the relay curve and the fuse curve for the downstream fault magnitude of 1,613 amps. The IEEE extremely inverse characteristics formula is as follows, where A equals 28.2, B equals 0.1217, and P equals 2. Plugging the values into the formula, we calculate that with a time dial setting of 0.12, the relay will operate in 0.4199 seconds, which will provide the desired selectivity with the downstream fuse curve. We will now determine the settings for the F60 I phase TOC pickup. Note that the CT ratio is 1200 to 5. Therefore, 1 per unit for this relay is 1200 amps. We will assume bus 2 and bus 3 have a maximum load of 5 MVA each. Therefore, the maximum load current is calculated to be 524 amps. The minimum pickup current for the time over current element will be 1048 amps, which is 2 times the maximum load current, or 0.873 per unit. With reference to Table 1, the maximum downstream fault current for this relay is 2,133 amps. Performing the same checks as was done with the TOC pickup of F60 II, F60 I's pickup was found to be acceptable. To ensure that F60 I can act as a backup for F60 II, the minimum fault current magnitude at the end of the F60 II's zone of protection is compared to F60 I's pickup. A minimum fault current of 1,290 amps at location F4 is greater than F60 I's pickup, and so F60 I can act as a backup for F60 II. Now we will determine F60 I's phase TOC time multiplier. For the fault current of 2,133 amps, F60 II's operating time is 0.2363 seconds. Earlier in the course, it was determined that a minimum discrimination time of 0.3 seconds should be used between microprocessor relays. As a result, for a 2,133 amp fault current, F60 I should operate in 0.5363 seconds, which is the sum of F60 II's operating time of 0.2363 seconds and a discrimination time of 0.3 seconds. We again use the IEEE extremely inverse formula and work backwards from the desired operating time of 0.5316 seconds, where A equals 28.2, B equals 0.1217, and P equals 2. Plugging the values into the formula results in a calculated time dial or time multiplier of 0.06 for the F60 I relay. We will now look at the phase instantaneous overcurrent settings for both the F60 I and F60 II relays. For feeder applications, if the ratio of the close-in fault to the far-end fault is 1.25 or greater, the phase instantaneous overcurrent element is used in conjunction with the time overcurrent element. In the case of F60 II's zone of protection, a close-in fault at F3 will result in a fault current of 2,133 amps, while a far-end fault at F4 will result in a fault current of 1,613 amps. The ratio of the close-in to the far-end fault is greater than 1.25, and so the instantaneous overcurrent element will be required. The phase instantaneous overcurrent will be set to operate at 85% of the maximum fault current to account for errors. As for relay F61, it can also be seen that the ratio is also greater than 1.25, and so the phase instantaneous overcurrent function will also be required and will again be set to operate at 85% of the maximum fault current of 3,347 amps. We will now determine the neutral definite time overcurrent for F62. Since we don't have a dedicated ground CT, we will use the neutral definite time overcurrent element. It should be set to 25% of the phase overload current, or 131 amps, which is 0.22 per unit. The delay should be set greater than 2 cycles to ensure that a transient condition will not cause its operation. Therefore, a value of 40 milliseconds will be chosen. Now let's determine the neutral definite time overcurrent for F61. Again, because we do not have a dedicated ground CT, we will use the neutral definite time overcurrent element. It should be set to 33% of the calculated phase overload fault current, or 131 amps. This is calculated as 0.11 per unit for this relay because of the differing CT ratio. Due to this relay being used as the backup for F62, the delay setting will be slightly greater. The delay should be set greater than 2 cycles. We will use a setting of 60 milliseconds. Now that we've made the calculations and entered the setting for the elements in our protection and control solution, we will look at the Flexlogic of the elements being used. We'll start with the functions of the inputs to the phase TOC element. The enable input is changed through the software or keypad to the enabled state. There is a bit that can be specified to act as a block for each phase, which we will not use. The user must specify the current source and whether or not voltage restraint will be used. We will not be using voltage restraint in this application. The only output that will be required by the Flexlogic is the phase TOC operate bit. Now let's look at the function of the inputs for the logic diagram of the phase IOC element. The enable, block, and current source inputs are the same as the TOC inputs. The only output that will be required by the Flexlogic is the phase IOC operate bit. The enable and block inputs for the neutral TOC element are configured the same as the phase overcurrent element inputs. The only neutral TOC element output that will be required by the Flexlogic is the neutral time overcurrent operate bit. Now let's take a look at a block diagram of the Flexlogic solution for this application. The manual close signal passes through to the virtual output to close an output contact to send a close command to the breaker. The phase time, phase instantaneous, and phase neutral overcurrent operate bits, in addition to the manual trip input, are ORed together to provide the trip command. Each of the selected phase and neutral overcurrent elements first pass through a positive edge-triggered one-shot and are then ORed together. The output signal of this OR gate then passes through a timer to ensure that the oscillography trigger bit, virtual output 64, will receive a maximum of 1 trigger every 500 milliseconds. As a final step, we should look at how the oscillography will be configured. Notice that the trigger source has been assigned to virtual output 64, which transitions to a logic 1 state for 1 scan under any overcurrent condition. This is the final Flexlogic equation that will be programmed into F60 I and F60 II. Note that the operate of each overcurrent condition is fed through a one-shot to the oscillography trigger. Microprocessor-based directional elements can operate under many different principles. We will now look at an example of a more popular approach to better understand directional elements. Directional overcurrent elements are used in many places on transmission and distribution circuits. The time and/or instantaneous overcurrent element are blocked by the directional element until the fault current is flowing in the tripping direction to prevent any false operation. A simple example of an application of directional element can be illustrated at our industrial customer site. If this customer supplements his power requirements by paralleling a utility supply with on-site generation as shown, he needs to have a directional overcurrent element on 52-2 breaker for the following condition. For fault at F1, which is fed by the generation system has to be isolated from the fault as fast as possible and still continue supplying the loads on the feeders. This can be accomplished only by detecting a reverse fault condition on breaker 52-2. To avoid a false trip, the protection requirement for this application requires that the time and instantaneous overcurrent elements be able to distinguish the direction of the fault. We will now explain the theory of directional overcurrent elements and then apply them to our protective solution. Loads are generally resistive, and so the current stays close to being in phase with the voltage and has a power factor close to unity. When a fault occurs, the fault current will generally lag the voltage by an angle of 80 to 85 degrees for a phase fault near a generator. This angle reduces as the fault moves away from the generator due to the feeder impedance having more of an effect on the phase angle. The typical phase angle between the current and voltage for open-wire transmission lines in a distribution system is as follows: 7.2 kilovolts to 23 kilovolts with a 20 to 45 degree lag. 23 kilovolts to 69 kilovolts with a 45. The directional element needs to have one polarizing quantity, one reference quantity that doesn't change during faults, and one operating quantity which does change during faults. Generally, the directional element uses a voltage vector as a reference quantity. The direction of a fault can be determined by comparing this reference quantity, which is the voltage phasor, to the operating quantity, which is the current phasor. The angle between them determines if the fault is in the forward direction or the reverse direction. We will only examine how the phase directional overcurrent detection method is applied to phase A. The same methodology is used on phases B and C at the same time. Comparing quantities. In order for a phase directional element to work properly, the element needs a reference quantity, either the voltage or current phasor, which will not change direction or disappear during a fault. Since the element is looking at phase A current, the element will use the phasor VBC as the reference because this phasor does not use any quantity from the potentially faulted phase A to create the reference phasor. The element usually allows the user to program an offset from this reference voltage vector for dependable operation, which was known as maximum torque in electromechanical relays. The protection engineer must look back into the system and determine what he expects phase A's current to be at the time of fault with respect to the voltage van. Let's say for this example the engineer expects a 60-degree lag between phase A's voltage and current at the time of fault. This would translate into a 30-degree lead or offset in the angle between phase A's current and the reference vector VBC. Within the element, there is a setting for this angle or offset. In modern microprocessor-based relays, this is referred to as the element characteristic angle, or ECA for short. The 30-degree lead is then entered into the directional element. Since counterclockwise rotation is considered forward, the angle of 30 degrees is entered as a positive angle. Again, this is the phase A's current angle relative to the reference phasor VBC that the element should expect to see at the time of fault. The relay then calculates a plane plus and minus 90 degrees from the element characteristic angle, which becomes the operating characteristic. One side of this plane is referred to as the forward direction, while the other is referred to as the reverse direction. Another way of looking at this is the ECA is the angle by which the polarizing voltage is shifted in the leading direction to achieve dependable operation. The rule of thumb for setting the ECA angle is around 30 degrees for simple feeder applications without a transformer in the protection zone, and around 45 degrees when a transformer is in the protection zone. Microprocessor-based relays will have other settings for the operate characteristic for added security, such as a pickup level for the current and a minimum level for reference voltage phasor. To support the generator that has been added to the system, we will now look at the elements and settings that will be required to add directionality to the phase time, phase instantaneous, and neutral time overcurrent elements used in our earlier solution. This is the block diagram of the directional element that is within the F60 universal relay. After examining the logic of this element, the protection engineer determined that the phase directional block output operand will be at logic 1 when the current is in the reverse direction, and so it will be used as a block signal for the overcurrent elements. We will begin by setting the phase directional element within the F60 relay. The signal source setting selects the current source and polarizing. The ECA setting is used to select the element characteristic angle, which is also known as the angle by which the polarizing voltage is shifted in the leading direction to achieve dependable operation. As stated earlier, the rule of thumb for setting the ECA angle for feeders with a transformer in the protection zone is around 45 degrees, so 45 degrees will be entered. The polarizing voltage threshold is the minimum voltage for which the phase angle measurement will be reliable. This value can be chosen as small as 5% of nominal voltage. In our example, we will select 5% by entering 0.05 per unit. A voltage memory feature is incorporated to increase security for three-phase faults very close to the VTs, which are used to measure the polarizing voltage. This feature stores the polarizing voltage the moment before the voltage collapses. This is then used to determine direction. The voltage memory remains valid for 1 second after the voltage has collapsed. The block when voltage memory expired setting is used to select the required operation upon expiration of voltage memory. Settings are yes or no. When set to yes, the directional element blocks the operation of any phase overcurrent element under directional control after the voltage memory expires. When set to no, the directional element allows tripping of phase overcurrent elements under directional control after the voltage memory expires. We will set this option to no. To add directionality to the phase time overcurrent element, we will set each of the phase block inputs of the time overcurrent element to the phase directional block output operand of the directional element. To add directionality to the phase instantaneous overcurrent element, we will again set each of the time overcurrent element's phase block inputs to the phase directional block output operand of the directional element. So far, we have focused our discussion on the phase fault overcurrent protection. In this system configuration, we might face the problem of direction with ground faults. For this reason, the F60 includes a neutral directional overcurrent element. The outputs from this element are asserted if the magnitude of the operating current is above the pickup level and the fault direction is seen as forward or reverse. It is important to note that the ground neutral overcurrent element should be set above any maximum unbalanced load current. The following are the setting parameters for the neutral directional element. The neutral directional overcurrent 1 polarizing setting selects the polarizing mode, voltage 3V0 or current 3I0. In most cases, and for our example, the polarizing quantity is voltage. The neutral directional overcurrent 1 polarizing voltage setting selects the polarizing voltage that will be used, which can be either supplied externally by connecting a broken delta PT, or derived from the calculated zero-sequence voltage from the phase PTs. In many cases, as in ours, calculated will be used. The neutral directional overcurrent 1 operating current setting allows for more sensitive setting by counterbalancing spurious zero-sequence currents resulting from system unbalances during heavy loads, CT errors during phase-to-phase and three-phase faults, or switch-off transients during phase-to-phase and three-phase faults. The selections are measured ground current, IG, or calculated zero-sequence current, 3I0. We will use calculated zero-sequence current, 3I0. The neutral directional overcurrent 1 positive sequence restraint setting offers restraint to the neutral directional overcurrent element where power system unbalances causes a presence of a certain amount of zero-sequence current. The element allows you to enter a restraint current calculated as a percentage of positive sequence current to ensure there isn't a maloperation of the element due to unbalance. This value is usually set around 6.25%. The neutral directional overcurrent 1 offset setting is used mainly in series compensated lines to guarantee correct fault direction. We won't consider this in our application. The neutral directional overcurrent 1 forward ECA setting defines the characteristic angle for the forward direction in the voltage polarizing mode. The current polarizing mode uses a fixed ECA of 0 degrees. As stated before, since the transformer is in the zone of protection, an angle of 45 degrees will be entered. The neutral directional overcurrent 1 forward limit angle setting defines a symmetrical limit angle, meaning both directions from ECA for the forward direction. To avoid nuisance operation at the boundary, the limit angle will be set to 80 degrees. The neutral directional overcurrent 1 forward pickup setting defines the pickup level of the current in the forward direction. This is set to the minimum neutral current level that the element is to operate on. In the case of a ground fault, it can be set to as low as 10%, but should be set above maximum unbalanced current, which is lower than 10% in this application, and so a setting of 10% will be used. The neutral directional overcurrent 1 reverse limit angle setting defines a symmetrical limit angle, meaning both directions from ECA for the reverse direction. To avoid nuisance operation at the boundary, the limit angle will be set to 80 degrees. The neutral directional overcurrent 1 reverse pickup setting defines the pickup level for the current in the reverse direction. Again, this is set to minimum neutral current, and in the case of ground faults, it can be set to as low as 10% or 0.10 per unit, but should be set above maximum unbalanced current, which is lower than 10% in this application. The neutral time over current can be modified to support directionality simply by using the directional element's forward or reverse operate bit as the input operand to the element's block input. The Synchrocheck function will be required by this application to ensure that the 52-2 breaker is closed only when the phase angle, frequency, and voltages on both sides of the breaker are within acceptable limits. Synchrocheck verifies that the voltages, V1 and V2, on the two sides of the supervised circuit breaker are within set limits of magnitude, angle, and frequency differences. The Synchrocheck function is intended for supervising the paralleling of two parts of a system, which are to be joined by the closure of a circuit breaker, as is the case at breaker 52-2. If one or both sources are de-energized, the Synchrocheck programming can allow for closing of the circuit breaker using undervoltage control to bypass the Synchrocheck measurements. Typical settings for the Synchrocheck are as follows: 10% difference in voltage, a maximum of 0.1 frequency difference, and a maximum phase difference of 30 degrees. The Synchrocheck 1 V1 source setting selects the source for voltage V1. The Synchrocheck 1 V2 source setting selects the source for voltage V2, which must not be the same as used for the V1. The Synchrocheck 1 V2 maximum voltage difference setting selects the maximum primary voltage difference in kilovolts between the two sources below, which is within the permissible limit for synchronism. The Synchrocheck 1 maximum angle difference setting selects the maximum angular differences in degrees between the two sources. An angular difference between the two input voltage phasors below this value is within the permissible limit for synchronism. We will use 30 degrees. The Synchrocheck 1 maximum frequency difference setting selects the maximum frequency difference in hertz between the two sources. A frequency difference between the two input voltage systems below this value is within the permissible limit for synchronism. We will set this to 0.1 hertz. The Synchrocheck 1 maximum frequency hysteresis setting specifies the required hysteresis for the maximum frequency difference condition. The condition becomes satisfied when the frequency difference becomes lower than the Synchrocheck 1 maximum frequency difference. Once the Synchrocheck element has operated, the frequency difference must increase above the Synchrocheck 1 maximum frequency difference plus the Synchrocheck 1 maximum frequency hysteresis sum to drop out, assuming the other two conditions, voltage and angle, remain satisfied. We will use 0.06 Hz for this setting. The Synchrocheck 1 dead source select setting selects the combination of dead and live sources that will bypass the synchronism check function and permit the breaker to be closed when one or both of the two voltages, V1 and or V2, are below the maximum voltage threshold. A dead or live source is declared by monitoring the voltage level. 6 options are available. The first option, of none, disables the dead source function. The abbreviations for the rest of the options can be interpreted as follows: live V1 and dead V2, dead V1 and live V2, dead V1 or dead V2, dead V1 exclusive or dead V2, which means one source is dead and the other is live, and finally, dead V1 and dead V2. We will select live V1 and dead V2. The Synchrocheck 1 dead V1 maximum voltage setting establishes a maximum voltage magnitude for V1 in per units. Below this magnitude, the V1 voltage input used for Synchrocheck will be considered dead or de-energized. We will set this to 0.3 per unit. The Synchrocheck 1 dead V2 maximum voltage setting establishes a maximum voltage magnitude for V2 in per unit. Below this magnitude, the V2 voltage input used for Synchrocheck will be considered dead or de-energized. We will set this to 0.3 per unit. The Synchrocheck 1 live V1 minimum voltage setting establishes a minimum voltage magnitude for V1 in per unit. Above this magnitude, the V1 voltage input used for Synchrocheck will be considered live or energized. We will set this to 0.7 per unit. The Synchrocheck 1 live V2 minimum voltage setting establishes a minimum voltage magnitude for V2 in per unit. Above this magnitude, the V2 voltage input used for Synchrocheck will be considered live or energized. We will set this to 0.7 per unit. Now we will look at the Flexlogic examples being used within this application so you can see what has been built so far. The first is the directional overcurrent Flexlogic solution. Now, here is the Flexlogic solution that includes the Synchrocheck interlock, which allows a close command to be sent to the breaker. Both of these solutions are used by our example F60 relay to provide our protection and control solution. We will now illustrate how the auto reclosure function will be incorporated into our application example. When the auto reclosure operates, the sequence of tripping and closing the circuit breaker is called a shot. In the absence of field experience to the contrary, transient faults are assumed to last less than 15 seconds, and so a two-shot auto reclose is generally used in power system applications where there is susceptibility to transient faults. If the transient fault lasts for more than shot 2's dead time, the fault is classified as a permanent fault, and auto reclose goes into what is termed as a lockout stage. In applications where it has been determined through actual field experience that the transient faults can last longer than 15 seconds, a 4-shot auto reclosure scheme is used. Let's assume that feeder F3 is an overhead feeder, which is susceptible to transient faults and controls a 3-pole breaker. The desired operation of the protection is as follows. If a transient fault were to occur at F2 such that an overcurrent element within the F60 III relay operates and trips feeder 3's circuit breaker, the breaker will isolate the transient fault from the system and allow the arc caused by the fault to extinguish. After a specified dead time, F60 III's auto reclosure function will then send a close signal to the circuit breaker to restore power to the load. If the transient fault is no longer present, no further action will be required. Now let's see how we can apply the auto reclosure function to the F60 III universal relay. We will first take a look at the auto reclosure function within the F60 universal relay. This auto reclosure function can support up to 4 shots prior to locking out. Each shot has an independently settable dead time, meaning the duration for which the breaker remains open in order to allow the fault energy to extinguish. All of the following conditions must be met within the F60 before the auto reclosure scheme will operate. The AR function is enabled. The scheme is not in the lockout state. The block input is not asserted. The AR block time upon manual close timer is not active, and the circuit breaker is in the closed state. The auto reclosure scheme is initiated by the change in state from a logic 0 to a logic 1 of the operand selected as the initiate bit within the auto reclosure setup. This bit is driven by the trip signal from the protective solution. In our example, the phase or neutral overcurrent elements operation will cause virtual output 63 to go to a logic 1 state, which will trip the breaker and initiate the auto reclosure. The maximum number of shots will be set to 2. The manual close input signal address on the UR will be specified. The breaker closed input signal address on the UR will be specified. The breaker open input signal address on the UR will be specified. The block time upon manual close will be set to 10 seconds. The dead time for shot 1 will be set to 0.5 seconds, and the dead time for shot 2 will be set to 15 seconds in addition to enabling the events. The auto reclosure indicates its state by setting the following internal operands to a logic 1 state. Reclose enabled means the scheme is enabled and may reclose if initiated, and all the applicable conditions are met. Reclose disabled means the scheme is disabled. Reclose in progress means an auto reclosure has been initiated, but the breaker has not yet been signaled to close. The reclose locked out means either the scheme has generated the maximum number of breaker closures allowed for a fault, or the scheme has been locked out externally. In addition to this, the scheme may also be sent in lockout when incomplete sequence timer times out, or when a block signal occurs while in reclose in progress. The auto reclosure scheme must be reset from lockout in order to perform auto reclosure for further faults. This would normally be accomplished automatically through Flexlogic. Incomplete sequence time is a timer which defines the maximum time interval allowed for a single reclose shot. It is started whenever an auto reclosure is initiated and is active when the scheme is in the reclose in progress state. If all conditions allowing a breaker closure are not satisfied when this time expires, the scheme goes to lockout. After examining the logic of this element, the protection engineer determined that the auto reclose close output operand shown here will be required to add auto reclosure to the Flexlogic solution. This is the block diagram of the Flexlogic, which includes the auto reclosure. Note that either the auto reclose operand AR close can be initiated internally by the relay or by the external manual close command. If either of these two conditions is met, a signal will be sent to the virtual output. The virtual output of this OR gate must pass to an AND gate along with the Synchrocheck permission signal before initiating a close output contact.